Hi, I am Yichun Zhou, and this is my demo for the final exam. And so the first part, I would like to demonstrate how the finite state machine works in the first part. So basically, we start with ACK equals 0 as well as go equals 0. And if the rack bit is set high, which indicates the calculation has begun, we will set the go bit to 1. And as long as the calculation is not finished, we stay in the state 1, which is the current state in here. And if the calculation is finished, we'll set ACK bit high and go bit back to 0. This indicates we no longer continue that calculation and the result is ready to view. And so basically the upper triangle is really the first parts, or say the first calculation. And if we go on for the second calculation, it is indicated by setting the rack bit back to 0. And in this case, we move from state 2 to state 3. As long as the calculation is not over, we stay in here. If the calculation is over, we set both speed back to 0, which indicates the result is ready to view. And then we have back at the starting state, and then everything is just like again. And so, by the way, I'm using one-hot encodings, which I think is a little bit of simpler, which would simplify my calculations. And so the circuit is in here. So basically all those formulas in the circuit is coming from the assignment table, which is available in the reports right in here. So the D flip-flops are basically just using for synchronization purposes. And if we go to the test bench, if we start taking the clocks, and then at this point, if we set the rack bit high, after some moments, yeah, at this point, the calculation is over. So the ACK bit is set to high. And then if we change the number in here and set it back to 0, after it finished the calculation, the ACK bit should be set to 0. So the LED in here should be back to black. To speed up, I would let the tick frequency go up a little bit. Yeah, in here. So it is back to 0. So this part of the circuit, I think, is they're probably working. And so if we go to the data pass part, so I'm not using a controller because I think the control path of this design assignment is pretty much trivial. So what I'm doing here is like, I'm using a load signal. So the load signal is basically whenever we set the go signal high, it will only be high for one clock cycle. This is really for initialization purposes. And so, and we also have a counter in here to control the clock cycles. However, if this algorithm converges before we reach the maximum, which is 255, we will also set the ACK bit high and put the whatever result is available to D out. And so at this part of the circuit, we can see that this is really for initialization purposes. So to initialize, we have the I, which is the iterator, initialized to 0, and we slowly increment it. This is the next I. This is the next I. So we slowly increment the counter if we go on looping. And then we calculate the square of I, which is the iterator here, and then we compare it with the D in. We do this comparison because we do not want to get negative numbers. So basically, if as long as we have this bigger, smaller, or equal signal, we can decide D in and I square which is bigger, and we decide we use which of the number to subtract the other. So this is basically the subtraction. the idea is in here, we get the difference between I squared and D in, and then we compare it to the previous clock cycles differences between the previous I squared and D in. And then we decide whether it is better. If it is better, we will update the value in here. If it is better, we update the value. If it is not better, we just we'll choose the previous difference value as the next difference. And so make all of those things work. When we plot the difference value, we would make it into the maximum integer available. And this is the last part. So I'm sorry. So basically what I'm trying to do in here is know that because we iterate from 0, the circuit should perform better and better. If it is not performing any better, we should probably stop, because it is likely that we have already reached the optimal value we can reach at this case. So basically, we decide if it is equal or any better is available. If either of this happens, we decide that we no longer need to loop around further, so we stop in here. And then otherwise we'll log the value which becomes available in here. So basically, otherwise we increment the iterator. Also note that the final D out result is really the iterator at last. So basically, if we try to test the circuit, so I would reset the simulation, start ticking. And we set the rack bit high. And in this case, we know that this is this is definitely the correct answer. 8 squared is 64, which we cannot get any further. In this case, yeah, this also converges, so I should probably change another value. Yeah. So 9 squared is 81, which is also closest to 78. If we try another extreme value, which is 25, sorry, which is set this low. So this is one of the extreme value I can get. This result is 255, and at this point, ACK bit is back to low. So if we try another value, for example, if we try 16, this is exact square root. It's not approximation. It gets 4. So I think in case that there is nothing wrong with the testing with common line, I think my circuit should probably work fine. But if there is anything wrong, I'm just trying to have this video recording to get some partial credits. And just in case you want to have a look at how the lot signal works, in here, like how this sub-circuit works, it is in here. So basically, the lot signal will only be high whenever the go bit is high. No matter how many cycles the go bit is high, the lot signal will always be high only for 1 bit. So this is really similar to what I would do in design assignment 2, task 1, I think. Yeah, so basically it's doing the same thing, but yeah, so I think, so for example, and this is also coming out of the assignment tables I had. Yeah, so I think that's probably all.